In this video, we're going to talk about the size of our atom, so atomic radii, ionization energy, and then also electron affinity energy. So atomic radii first. So a couple trends on the periodic table, and I do want us to know the reason for these trends. I am probably more likely to ask you why potassium is larger than sodium than I am to ask you which one is larger. So please be able to explain the trends. And then just like we were doing with quantum numbers, the periodic table is never going to be our answer. If you say because it's further down in the periodic table, well, that's how we're going to remember it, right? The periodic table is our tool, but that's not our answer, right? Potassium doesn't consult the periodic table to see what size it should be. So be really careful to not use trends or your tool as your answer. Right? 4 plus 4 doesn't equal 8 because your calculator says so, right? The calculator is the tool that gives us the answer, but it's not the reason for it. So again, just be really careful when answering these questions. So atomic radii, I am going to give us a trend, but I want us to be able to explain that trend. So within a group on the periodic table, remember our groups are our columns. Our radii get subsequently larger as you go down a group. So again, this is how we're going to remember it, but again, it's not our reason. Our reason, if we look at our periodic table, and I'm just going to look at group 1, which I can't spell, group 1, or 1A, I have hydrogen, lithium, sodium, potassium, it goes on, but this is enough to make my point, and our atoms are actually getting larger as we go down. Our reason is the number of occupied shells, right? If I was to write the electron configuration for hydrogen, 1s1, if I was to write it for lithium, 1s2, 2s1, sodium, 1s2, 2s2, 2p6, 3s1, potassium, 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. So if we look at our highest energy level that's occupied, right? With hydrogen, it's the first shell. With lithium, it's the second shell. With sodium, it's the third shell. And with potassium, it is the fourth shell. If we were to add rubidium, it's going to be the fifth shell. Cesium is going to be the sixth, and so on. And remember, as our value for n gets bigger, its extension into space gets bigger. So that's our reason, right? Hydrogen, my highest occupied shell is shell 1. With potassium, my highest occupied shell is shell 4. The bigger the shell number, the larger its extension into space. So as we go down a group, right, successively we could, let's say, successively larger energy levels are occupied with electrons, right? Remember, as the value for n gets bigger, the extension into space, right, its distance from the nucleus, increases. So it's not that potassium is below hydrogen in the periodic table, it's that potassium, I'm occupying the fourth shell, and hydrogen, I'm occupying the first shell, and the fourth shell is much larger, right? It extends further into space than the first shell does. So as we go down a group, successively larger energy levels are occupied with electrons. right? As our value for n gets larger, its extension into space, its distance from the nucleus, its radius is going to increase. So that is our reasoning. I'm also going to give us a trend as we go across a period of the periodic table. So this was going down a group, and then as you go across a period, those were our rows, remember? Atomic radii are actually getting smaller. And I'm really going to just look at main groups. Remember, our main groups were our A block, so 1, 2, and then 13 through 18. And again, this is just the trend that helps us remember it. The reason is not going to be the periodic table, right? I do want us to know the reason, so we're going to look at that. And let's look at carbon. I'm just starting part way across. Actually, let's just do a couple. Let's do lithium. I'm looking at period 2. So we'll look at lithium. I'm going to look at carbon, and then we'll look at fluorine. So I'm just picking a couple as we go across. And again, I'm going to draw my electron configurations. So 1s2, 2s2. Oops, sorry, lithium. I'm getting crazy. 1s2, 2s1. Carbon, 1s2, 2s2, 2p2. And then fluorine, 1s2, 2s2, 2p5. So my highest occupied shell for all of these is 2. If I'm in the same period, right, the same row, I'm not occupying a different size shell, right? As we go down, larger and larger shells are occupied with electrons, right? If I look back up at this trend, I'm going from shell 1 to shell 2 to shell 3 to shell 4 as I go down. As I go across, my shell stays the same, right? Lithium, carbon, fluorine, everything in period 2 is going to have n equal to 2 as its highest energy shell. So that can't be our reason, right? We can't say, well, I'm adding electrons to smaller shells or something to explain why it gets smaller. Like, that doesn't work. So what we're going to look at here, I have to give us a new term, is our effective nuclear charge. And we're going to use this term when we talk about ionization energy also. And our abbreviation for effective nuclear charge is a capital Z and then an EFF. And I do cross my Z's. I may have said this before, but this is how I make a 2. And then let's not cross it. This is how I make a Z if I don't cross it, and it's really impossible to tell. So I will cross it so you can tell the difference. So that is a Z, and then a subscript EFF. Sometimes we'll just call it Z effective. The proper name would be effective nuclear charge, but Z effective is a okay way to call it. And what this is it's my nuclear charge, which is just plain Z, and I will define these, minus what's called shielding. And that's going to equal my effective nuclear charge. So as I go across, what's happening is my effective nuclear charge is increasing. You can really think about effective nuclear charge as the amount of the attraction. And this isn't really kind of the definition, but this is how I like to think about it to be able to explain it. This is going to be the attraction that the outermost electrons feel for the nucleus. Right? If I was to define effective nuclear charge, what I gave us originally, right, Z minus shielding is our way to calculate it. It's also kind of a way to explain it, but if I wanted to just put it kind of in one sentence, it's effectively, right, the attraction that the outermost electrons feel for the nucleus. So if I was to look at lithium, lithium has 3 protons in the nucleus, so a +3 charge. And then I have an energy level that has 2 electrons in it. They're both in my s orbital. And then I have another energy level with 1 electron in it. So what shielding is the repulsion felt by inner shell electrons. So remember, our nucleus has a positive charge, my electrons have negative charges. So all of those electrons are attracted to that nucleus. However, this electron is actually slightly repelled by those electrons. So this electron out here in the outermost shell doesn't feel the full attraction to that nucleus that it would if those inner shell electrons weren't there. So essentially these repel the outer shell electron, which we do have a special name for. So by it I mean the outer shell electron, doesn't feel the full attraction. Right? If I was to get rid of those 2 inner shell electrons, it would be more attracted to the nucleus than if they are here because they're repelling it, right? They're actually pushing it out a little bit. There's some repulsion there. So these repel the outer shell electrons, so the outer shell electrons don't feel the full attraction for the nucleus. So shielding, this is that repulsion due to the inner shell electrons. What my nuclear charge is we can just think of this as the attraction that the electrons have for the nucleus. So our attraction, and this is just kind of a shortcut way to estimate it. This isn't actually how you calculate it, but it's how we're going to look at the relative effective nuclear charge. So my attraction, I would say, okay, in lithium, I have 3 positive charges and I have 3 negative charges. So I'm going to say that my attraction is 3. So that's going to be Z. I have 2, sorry, this is getting so messy, 2 inner shell electrons. So that's my shielding. And then that's going to give me a relative effective nuclear charge of 1. If we look at carbon, I have 6 electrons total. So that's going to be my Z, right? My attraction. I have 6 positive charges. I have 6 negative charges. So those groups of 6 things are all attracted to each other, right? 6 electrons being attracted to 6 protons. If I look at my inner shell electrons, be really careful now. Shells are my values for N. So this is my inner shell. All of that is my outer shell, right? I have 2 of them in an S subshell. I have 2 in a P subshell, but because this has a 2 and this has a 2, they're both in that second shell. They're just divided into different subshells. And then these are actually divided into different orbitals, right? 1 in each, because we follow Hund's rule. So I actually have 2 inner shell electrons still. And that's going to give me 4. And again, this is just relative. So what I'm saying is that the attraction between the electrons and carbon, right, because that's what my Z effective is telling me, is bigger than my attraction that the electrons in lithium have for the nucleus. And if we were to look at fluorine, again, I have 2 inner shell electrons. These are all my outer shell electrons. So I have 9 electrons total, if you were to add those all up. I have 2 of them in an inner shell, so that gives me an effective nuclear charge of 7. So the electrons in fluorine, again, remember what my effective nuclear charge is telling me, the electrons in fluorine are more attracted for the nucleus. So how does that relate to atomic radii? Well, Well, as I go across the periodic table, those outermost electrons are more and more attracted to the nucleus. Because of that, it actually gets pulled in a little bit closer just because of the charge. If you were to take two weak magnets and try to hold the opposite poles next to each other, nothing really happens. If you were to take two strong magnets and kind of hold them close to each other, you can feel them getting pulled in. And this isn't magnets, it's charge, but it's the same sort of idea. As my charge gets greater, it's more attracted. So our reasoning, as you go across the period, more protons and electrons are added to the atoms. Right? If we go back and look at our example here, I had 3 protons, 3 electrons. Carbon, I had 6 protons, 6 electrons. Fluorine, 9 protons, 9 electrons. So as I go across the period, more protons and electrons are added to the atoms. But shielding does not increase. Right? They have the same number of inner shell electrons. Right? If I look, my number of inner shell electrons is 2 for all of those. So the effective nuclear charge, the effective increases. Or so's. So the outer shell electrons are pulled in a little closer to the nucleus, right? More attraction. So as I go across the period, more protons and electrons are added. Shielding, however, does not increase. So I have more total electrons, but my inner shell electrons are the same. So I have a larger effective nuclear charge, right? I have more attraction between those outer shell electrons in the nucleus, and it's pulled a little closer to each other, right? If we wanted to look at fluorine, let me make it a +7. Oh, 9, what am I thinking? +9, right? 9 protons. And I have 2 shells. Again, they're divided in subshells, but I have 2 electrons here. And this is a horrible picture because this is not at all what it looks like. But I would have 7. They're not in the same region of space. Remember, we can never have more than 2 in the same region of space. These are in the same shell, but different subshells, different orbitals. 1, 2, 3, 4, 5, 6, 7. 7 of them. So essentially, I have these 2 repelling those 7, right? When I looked at lithium, which is a mess up here, let's get rid of some of this marks. I had those 2 repelling 1 electron. So more attraction here. And again, this is not what my atom looks like. I really can't handle it, so we'll just cross it off, right? I don't have all those electrons right next to each other, but they are in the same shell. Different subshells, different orbitals, right? If we go and look, I have 2 of those 7 electrons are in an s orbital, and then I have 3 p orbitals, and 2 of them have 2 electrons in it, and 1 of them have 1 electron. So again, we can use the trend to help us remember the order, right? If I give us an example and I say, which of the following atoms is larger? Has the larger radii? And we can look at phosphorus or chlorine. So those are my choices. by all means, use the periodic table as your tool, right? You can use your calculator if I gave you a math problem, so by all means, use your periodic table. Phosphorus is going to be the larger one. If I asked you why, however, right, these guys are in the same period, so you're going to use this explanation, right? We're going to talk about how we have more total electrons, but we don't have any more inner shell electrons. So, and that's in chlorine, right? Chlorine has more total electrons, but it has the same number of inner shell electrons as phosphorus. So its effective nuclear charge is greater and it's pulled in a little bit, making its radius smaller. So by all means, use the periodic table to help you decide, but then when you explain it again, don't use the trend as your answer. I will give you no partial credit for that, like complete zero, right? That is not our reason, it's just plain wrong. So be careful. I say this every semester and then someone still gives me the periodic table as the reason. It's not our reason. So please pay attention. I am likely to ask why, so watch out for these. So ionization energy next. And our abbreviation for ionization energy is a capital E with a subscript lowercase I. And ionization energy is defined as the amount of energy needed to remove an outer shell electron from our atom. The amount of energy needed, and we could just say any electron. We're not actually going to remove inner shell electrons. We'll draw electron configurations actually in the next chapter for ions, things that have electrons removed from them. So the amount of energy needed to remove any electron, it will be from our outer shell. I guess I can't resist. From an atom. So kind of an example, and I'm just going to write energy. I don't actually have the value with me. But if I was to take chlorine and I was to add energy to it, I can remove an electron from it. Remember, if we lose an electron, it has a positive charge. And then we have that electron. It didn't just disintegrate, so it's there. This energy, right, the amount of energy that I need to do this is my ionization energy. So we take an atom, we add energy to it, we remove an electron. The amount of energy that takes is my ionization energy. And as you can imagine, some atoms it's easier and some atoms it's more difficult to remove electrons from them. So kind of in general, the more tightly the electron is held, the more difficult it is to remove it. Which just makes sense in everyday life, right? If something is held really tightly, it's harder to remove it. So the more tightly the electron is held, the more difficult it is to remove it. Lots of so's, so more energy is needed. Right? We're going to have a higher ionization energy if it's held tightly, right? If something's stuck, you have to put a lot of effort into removing it. So the more tightly the electron is held, the more difficult it is to remove it, so the more energy is needed, right? Higher ionization energy. It's kind of a funny looking eye. That didn't really get any better. The other way you can look at it is that if things are more stable, they don't want to become less stable. So if it's more stable, right, with the electron, it's going to be more difficult to remove the electron. Again, higher ionization energy. There is a trend on the periodic table. There's a couple trends. The one going down, we can do that one. Going across the periodic table, there's so many exceptions. I don't even really want to consider it as a trend. Again, just because there's so many exceptions. So if we go down a group, and we can look at the same ones we did before. I'm not going to do, we'll just kind of skip. So let's do hydrogen, sodium, and cesium. Right? If I have hydrogen, 1s1, I'm going to use my Nobel gas shortcut for these. So I have neon, and then 3s1. And then for cesium, I'm going to have xenon, and 6s1. So in hydrogen, I'm removing an electron from our first shell, right? N is equal to 1. With sodium, our electron is removed from N is equal to 3. And with cesium, the electron is removed from N is equal to 6. So is it going to be more difficult to remove an electron from the first shell or from the 6th shell? What do you guys think? Hopefully you said the first shell, right? Remember, the closer the electrons are to the nucleus, the more tightly they're held, right? The closer the electrons are to the nucleus, the more stable they are. So in hydrogen, right, that electron that we're removing, and again, this isn't to scale, but it's right there. If I was looking at cesium, it's right there, right? And again, not to scale, but it's much further away than it is with sodium, than it is with hydrogen, sorry. It's closer, it's further away than sodium, which is further away than hydrogen. Sorry, that got confusing. So the more tightly it's held, the more difficult it is to remove it. So as I go down a group, I actually have smaller ionization energy, right? Electrons are not held as tightly. If I'm up here, I have higher ionization energy because the electrons are held more tightly, right? They're in a smaller energy level, smaller shell. So this is just our old reminder. Remember, the closer the electrons are to the nucleus, the more tightly they are held, right? More attraction. We could also say they are more stable. We'll get rid of this parenthesis. So lots of dots. Higher ionization energy when they're closer, right? The closer the electrons are to the nucleus, higher ionization energy, right? It's more difficult to remove it when it's held tightly. It takes more of an effort, so I have to put more energy into it. Going across the periodic table, I just don't want us to look at the trend. I'm just gonna give you examples, and you really have to take it on a case-by-case basis because there's exceptions. So across the periodic table, there are exceptions to the trend. And the trend is never going to be our answer anyway, so it's better to just look at it on a case-by-case basis. If you wanted the general trend, this is excluding the exceptions, as you go in this direction, ionization energy is actually going to increase, right? Because in general, our effective nuclear charge increases, right? Sorry for that's pretty cryptic. So this arrow is saying as I go across the table, right, from left to right, my ionization energy in general, again, there's lots of exceptions, is going to increase. Our reason for that, the effective nuclear charge increases, and don't just say that, right? There's more attraction. So harder to remove it. you can think of your radii as actually being smaller. Right? So there's more attraction. But again, there's going to be a lot of exceptions. So just be careful to use that trend going across. I find that if people even consider that trend, then they miss the exceptions. So I wouldn't use that. You can use the trend down a group to help you. There aren't exceptions to that, so to help you remember the order. Again, that's not our answer to why, but you can help use it as your tool. Going across, I would worry about you not noticing exceptions if you rely on that trend. So an example, if I was to look at beryllium versus boron, and for any of these, so a typical question, I would say, which of the following has the higher ionization energy? Or I could say the smaller ionization energy. So be careful. If I say smaller ionization energy, I'm asking which one is it easier to remove the electron from, right? Just the opposite. So I would give you these two, and then you have to choose and then likely explain why. So beryllium, if I draw it to electron configuration, I have 1s2, 2s2, and then boron, 1s2, 2s2, 2p1. And then remember, for all of these, ionization energy means I'm removing an electron. So what I'm going to, those are just supposed to be arrows, not reaction arrows, which is why I made them look so funny. I'm going to 1s2, 2s1, right? I've lost an electron, so this is beryllium with a positive charge. Boron, I'm going to 1s2, 2s2, so boron with a positive charge. So what I'm losing with this one, right? I'm losing a 2s electron. Here I'm losing a 2p electron. Is it going to be easier to remove an electron from a p subshell, right? A dumbbell-shaped region of space, or from an s subshell, something that's spherical? Yeah, hopefully you said the p, right? It's going to be easier to remove it from this one. And then also the thing you want to remember filled subshells are more stable. I know half-filled I said too, but filled is actually better than half-filled. So if I look at this, I have a filled subshell now. Here I went from filled to half-filled, so not horrible. But on this one, I went from something that was neither filled nor half-filled to a filled subshell. So no matter how you look at it, boron's going to have the easier one. Beryllium has the higher ionization energy. And if you use the trend on the periodic table, you would be incorrect because boron is further across. But again, there's a lot of exceptions. If I was to compare nitrogen to oxygen, you would be wrong again using the trend. So just be really careful. So beryllium has the higher ionization energy, right? It's easier to remove the electron from boron because it's in a p subshell versus the s subshell with beryllium, right? Remember, electrons are centered around the nucleus in s orbitals, right? There's a node around the nucleus in p orbitals, right? Remember the energy of our subshells, s orbitals are lower in energy, right? More stable than our p subshells are. So it's easier to remove an electron from boron because it's in a p subshell versus the s subshell with beryllium. Electrons are centered around the nucleus in s orbitals, so that's why it's more difficult to remove it from beryllium. And then also, removing the one, I guess it's in 2p electron from boron gives it a filled subshell. Don't say shell because it's not a filled shell. I'd have to have 6 electrons in that p subshell to have a filled second shell. So watch out in your wording there. So removing the 2p electron from boron gives it a filled subshell. So this is a good thing. So it's easy to do. So this entire very wordy explanation is explaining why the ionization energy is lower for boron, leaving beryllium to have the higher ionization energy, right? Lower ionization energy for boron. And again, if you were to use that trend on the periodic table, you would get this one wrong. So just be really careful. It's just super easy if I give these two to you. Sorry, that was hard to say. And then you just look at the trend, you'll get it wrong. So I really just, it would be better to like not even look at that. Right? I had said nitrogen and oxygen. If I look at nitrogen and oxygen, and again, I'm going to draw electron configurations. If you get stuck, do that. So they're both 1s2, and then 2s2, 2p3, 2s2, 2p4. And then for our ionization energy, again, we're removing an electron. So I'm going to nitrogen with a positive charge, 1s2, 2s2, 2p2, right? I had 3, I removed 1, so there's 2 of them now. Oxygen with a positive charge, 1s2, 2s2, 2p3. So of these, which one's more difficult to do? Which one's going to have the higher ionization energy? What are your thoughts? If you said nitrogen, you are correct. If you were using that trend that I told us to ignore and scribbled out, so we're going to ignore the trend after I make this statement, you would be wrong because oxygen is further over. But if I look at oxygen, I'm actually going from a subshell that's neither filled nor half filled to a half-filled subshell. So I'm actually giving it relative stability when I do this. It still takes a lot of energy. We don't really think of oxygen as having a positive charge, but if I was to compare that to nitrogen, it's better, right? Nitrogen. Nitrogen had a half-filled subshell, and I'm messing that up. So like nitrogen had a little bit of extra stability, and I messed that up by removing the electron. So that was hard to do. Oxygen, it didn't have that. By removing the electron, I gave it that little extra bit of stability, so that's easier to do. So just be really careful. Don't use the trend as you go across. Look at the individual cases. Draw out the electron configurations, look to see where you're taking that electron from, and then be able to explain what's happening. If we were to remove more than one electron, they're actually all removed separately. So if I went from aluminum to aluminum with a +1 charge, and then the electron is by itself, that actually is going to take energy. And then I have aluminum with a plus charge. I remove a second electron. And then aluminum with a 3+ charge, 2+ charge, sorry guys. I remove another electron, and now I have 3+. And each one of these, it happens successively. So essentially I'm not going from aluminum to aluminum 3+. I'm not just taking all 3 at once. Each one has its own energy. So this would have ionization energy with a subscript 1, ionization energy 2, and then ionization energy with a 3. And the way we would say it, we would say first ionization energy, second ionization energy, and third ionization energy. If I don't specify, we're specifying first. So in these examples, because I went from the neutral atom to the +1 charge, and I did that for both of our examples, right, from the neutral atom to the +1 charge, we were looking at our first ionization energy. And again, if I don't specify, I'm asking for the first. If I was asking for the second, then you're going to start with the positively charged atom, right? And then we're going to go to the +2. If I wanted the third, start with the positively 2, right? It has lost 2 electrons already, and then remove that third. You can have a fourth ionization energy. Tin typically forms a +4 charge, so it loses 4 electrons. Each one of those removals has its own ionization energy associated with it. In general, as you go from first to second to third, the energy tends to increase. So my third ionization energy is always going to be larger than my second, which is going to be larger than my third. So successive ionization energies increase. Right, so the energy of my first ionization energy will be smaller than the ionization energy for the second, so my second ionization energy, which is smaller than my third ionization energy. So it does increase. The reason for this is pretty straightforward, actually. Most people overthink it, is that you're going from a neutral atom, right, something that doesn't have a charge, so it's neutral, and you're removing the electron. Remember, electrons are negative. For your second ionization energy, you're taking an ion that has a net positive charge and you're removing a negative charge from it. So it's just harder to remove a negative from something that has a net positive charge. Remember, opposites attract. So the fact that our entire atom has a plus charge, right, it's not neutral. The entire atom has a positive charge. It's more difficult to remove that electron. Third ionization energy, you're removing a negative charge from something that has a net 2+ charge, right? So we're taking something that's pretty positive and you're trying to remove a negative from it. That just makes it more difficult. So every time we remove an electron from something that's more and more positive, which is what we're doing with successive ionization energies, it just gets harder. So my ionization energies tend to increase. I want to talk about electron affinity energy next. Be really careful to not get ionization energy and electron affinity energy mixed up. I will make a big deal comparing and contrasting them after I go through our definition here. Our abbreviation is a capital EA. I have seen it abbreviated, a capital E with a subscript EA, and then I have seen it abbreviated a capital EA. I tend to use this version though. Also be careful to not get it confused with the electron negativity. Probably a lot of students do that, and it's probably because they sound so similar. So electron affinity energy and electronegativity are not the same thing. One has to do with bonding electrons. This one does not have to do with a bond. So be really careful. They're totally different concepts. So please do not get electron affinity energy and electronegativity and ionization energy confused, right? We need to learn our definitions here. So what this one is, this is the amount of energy released. So we're giving it off. So our values tend to be negative, right? Remember, negative sign in front of our energies mean energy is being given off, right? We can't have a negative magnitude. It's just the direction. So energy is being released. So the amount of energy released when an electron is added to an atom. So the complete opposite of ionization energy, right? With ionization energy, instead of releasing energy, you're putting energy into it, right? It takes effort. Instead of adding an electron, you're removing an electron. So this one, if I was to write a reaction, I could take sodium. I'm adding an electron. I'm going to end up with sodium with a negative charge because we added an electron to it. And then I'm going to release energy in that process. So energy is given off, right? It's a product. My electron is the reactant. So kind of just comparing and contrasting this, you just be really careful. Ionization energy versus electron affinity energy. Here we're removing an electron. Here we're adding an electron. Here energy is added. Here energy is released. If you were to look at values, you will actually find them as positive values, but what that means is that you just don't want to add an electron to it, right? It's cost prohibitive. If you want it to be favorable, it's going to be negative, right? A negative value is favorable. Here, a high ionization energy means it's difficult to do. So the electron's held tightly, it's really stable the way it is, it already has a filled subshell and we don't want to mess that up. If I have a high ionization energy, it's difficult to remove that electron. Maybe instead of saying to do, we should say difficult to remove the electron. If I have a high electron affinity energy, it's easy to add the electron. Because remember, we're releasing energy. Giving a lot of energy off is a good thing because we're becoming more stable. With ionization energy, we're adding energy to it, which means we're becoming less stable, right? So just be really careful. And it's not that the product is less stable, it's just adding energy to something isn't necessarily favorable. So ionization energy, we're removing an electron. If you have a large value, it means it's difficult to remove it. With the electron affinity energy, we're adding an electron. If you have a large value, it means it's easy. And when I say large, there is going to be a negative sign in front of it, right? Just be really careful from talking about energy. A negative 200 kilojoules is bigger than a negative 20 kilojoules, right? Number line way, no, but remember the negative sign doesn't have to do with magnitude, right? It has to do with the direction. So giving off 200 kilojoules is more favorable than giving off 20 kilojoules, right? The negative sign again is just our direction. And for these ones, again, I wouldn't look at trends. I would just look at the individual cases. To magnesium. So our question, which has the higher electron affinity energy? So sodium or magnesium. And then just be really careful. Higher means easier to add the electron. And I would almost write this on tests and quizzes. Like I would write that down for yourself, like have scrap paper if it's on Canvas and write that. Because if I ask the question, which has the higher ionization energy, I'm asking which is more difficult to remove. So higher ionization energy, difficult. Higher electron affinity energy, easier. Just be really careful. So if you have to write yourself this little note so you kind of know what you're looking at, please do that. So I'm going to draw my electron configurations. I'm going to use my noble gas shortcut. So I have neon and then 3s1, neon 3s2. And then we're adding an electron. So I'm going to sodium with a negative charge, neon 3s2, right? Because we added an electron to it. And then magnesium with a negative charge, neon 3s2, 3p1. So our question is, of those two, which one do we like better? Which one's more favorable? What do you guys think? If you were thinking sodium, you're correct, because we're filling that subshell, right? It was half filled, and half filled and filled are both more stable, but filled is going to be better. So because I'm completing that subshell, it's actually going to be better. If I look at magnesium, I had my outermost subshell filled, and then I just went and stuck one in a P, which is higher in energy. There's really no advantage to doing that. So sodium is going to have the higher electron affinity energy. Again, just be really careful to keep the two straight because they're completely opposite. And if you're, hurrying on a test, it's easy to get them mixed up. So I would write myself those little notes, kind of cliff notes, as to what's going on. If I said has the lower ionization energy, now I want what's easier to remove, right? I could ask them the opposite. So just be really careful on these.